Hi guys, let's see one more magnetic system which is known as solenoid. Solenoid is a magnetic system, it means which can generate magnetic field. Usually this kind of magnetic, magnetic coil, a coil which is extended with several loops. So this is one of the needed component in the electrical circuits to generate magnetic field in that corresponding situation. So usually it contains in televisions in the old sets. Right now everything become flat. We won't find this much complicated thing. Today we would like to how this component generates magnetic field. So let us see that. To describe this solenoid, so a solenoid just a insulated copper wire that is wounded closely in the form of an helix. It's an insulated copper wire wounded closely, just that forms an helix. Suppose if we can give current to this solenoid, so the current causes to create magnetic field. So here the current which is caused is just a direct current. So that direct current, DC current, is passing through solenoid. Then the magnetic field is generates the alignment of the magnetic field you can see in the given diagram. Now inside the coil the magnetic field lines are straight lines, just like they are entering one side of the solenoid to the another side of the solenoid, and outside the coil so they form a closed loops. So this is the one of the needed in the MRI scanning. So this is MRI scanning is used to diagnose the brain functions when it very abnormal situations, or nowadays it is necessary in the diagnosis of the cancer treatment, because the magnetic field which is generated by this machine and the corresponding magnetic field which respond in the human cells, so we will get an image, just like the cardiac graph, how it is helpful to diagnose the heart functioning. So like that, this magnetic map. Now this should contains a large powerful solenoid, so that is generates a very high amount of Teslas of magnetic field. So then we can get the image. Now this is the magnetic field directions. So the brightest lines inside the coil represents the strength of the magnetic field. Not only that, if you can closely observe at the each circle or each loop, again the concentric circles of the magnetic fields are generated. Now the combined of all the elemental length in the coil will gives the magnetic field at that corresponding point. And when you come far away out, when you move far away from the coil, the strength of the magnetic field is decreasing. So almost all we can take that as negligible. Almost all magnetic field goes to zero at the outside the coil. So here to find the direction of the magnetic field, usually we used to do the right hand thumb rule, Ampere right hand thumb rule. We can find the direction of the magnetic field. So this is the diagram which is given in your textbook. So be careful, the current direction and magnetic field direction. So how the magnetic field lines are passing from one side to another side. And here you notice certain spots. So these spots between the coils. So between the coils, if you can notice, that magnetic field is 0. So if you can take the right spot at here, which I am going to highlight with this pink color, the magnetic field in this region equal to 0. Yeah, that you can understand because of the two concentric circles are interacting at there. So the total fields gets cancel each other. And if you can notice the magnetic field at P region compared to Q region. So Q region, the magnetic field equal to 0 at most because there is no magnetic field line at there. But P, at point P, the magnetic field line's density is more. So here at point P, the magnetic field strength is more. So this magnetic field direction will change according to if you can change the direction of current in the coil. So current enters in one coil of one side and leaves in the current in another coil other side. So if you can draw, if the current is entering at here, so from this point it is coming out and it is leaving at there. And this coil is continuity to this another coil from inside. Now again the same current will be enter and it will be leave. So now this will be completes a closed circuit. So like this, the current is enters to one coil side and it leaves to another coils. So each time the direction gets changes. Now try to learn the magnetic field line patterns here carefully, and here the solenoid magnetic field line patterns is exactly equal to the magnetic field lines due to a bar magnet. We had a previous knowledge regarding in our lower sections. So we studied and draw the magnetic field lines due to a bar magnet. So solenoid magnetic field lines patterns and bar magnets magnetic field line patterns, they both are same. So this is the overall view from far point of the total solenoid. So here you can notice two things, the cross and dots in the coil itself. So here the coil is not drawn, just only the magnetic field lines are drawn. So the current enters in the plane of screen at points which is marked at here. So through these marks of cross, the current is entering. Current entering. And through the dots, the current is leaving. So now if you can draw the current direction of that coil, current direction. Why? Because I am stressing about the current direction. If the current direction is changed, the magnetic field direction also gets changes. And very important point I need to stress it here. So between the rings or between the coils, the magnetic field at here goes to 0. And the strength of the magnetic field is strongest between the coil, and that is also uniform magnetic field. And far away from the coil, the magnetic field strength goes to 0. So this is the pattern of the magnetic field and the direction of the magnetic field. Now here our task is to derive a mathematical expression. To derive a mathematical expression by using Ampere's law to this magnetic component or magnetic system. So if you recall the Ampere Circuits Law, so closed integral b bar dot dl equal to mu naught times I. By using this relation, I am going to find what is the magnitude of magnetic field relation in this solenoid. It's a very easy expression, it's not tedious. The only thing we need to concentrate much about the proper selection of Amperian loop. Let's try to derive expression for the magnetic field inside a long straight solenoid. So here, as per I said, the current entering and current leaving. So the cross are representing current which is entering through the coils, and dots are representing the current leaving the coil. So let me elaborate this. So this is a setup of a cross-sectional viewpoint of a solenoid. So here the coils are not drawn. Suppose if you draw a coil set here, then the diagram becomes very messy. So it's better to not to draw. So like this, we need to represent the corresponding coils and current direction, and from inside also we need to draw, because this is a helical loops. Now that presentation is not there. So the magnetic field inside closely wound long solenoid is uniform. So the inside region, so within this inside region, the magnetic field is uniform magnetic field. So the strength of the magnetic field in this whole region is uniform, because the coils are very close and the magnetic fields elements, they add up each other, so they can contribute the total magnetic field which is maximum. And the various turns, between the turns, the magnetic field equal to 0. Now to find the magnitude of magnetic field by using Ampere Circuits Law, we need to select a proper Amperian loop. So here the rectangle Amperian loop has been selected. So here ABCD is a rectangular Amperian loop. So for a particular portion, so he has taken this rectangular Amperian loop ABCD. So why here not selected the circular? So because to this system the circular Amperian loop is not a good choice. So according to the magnetic system, we need to change the Amperian loop. So this loop of side H. Now if you can apply the Ampere's law, closed integral b bar dot dl equal to mu naught times I. I is here current enclosed. I leave this I, current enclosed. Now here we need to figure out what is the closed integral of dl. So if we can do separately, now the closed integral b bar dot dl equal to, so we need to do the integration between closed integral from a to d, small a to d, b bar dot dl. So the small a to d we fragment into particular parts, that is closed integral a to b, b bar dot dl plus closed integral b to c, b bar dot dl, and plus closed integral c to d, b bar dot dl, and last closed integral d to a plus closed integral d to a. Everything is closed integral b bar dot dl. So this is what we did. How? the length of the elemental length is affected the magnetic field. Now if you remember, this is the dot product of B bar, magnetic field B bar, and elemental length. So that is the closed integral A to B bar dot dl bar equal to closed integral A to B. So that is dot product between this elemental length and magnetic field. So that I can write B dl cos theta, because B bar and dl bar both vector, the dot product of both vector, the formula goes to B dl cos theta. Here theta is angle between magnetic field B bar and elemental length dl. So this is a very key point at here. So the magnetic field direction and the elemental length, what we have chosen in the Amperian loop, that elemental length direction is needed to calculate the magnetic field in that particular portion. So here in this given diagram, the B bar is along in this direction. If I represent that with this bold ink, so this is magnetic field direction. So this is B bar. From the A to B, the elemental length direction, Amperian elemental length dl direction also in the same from the A to B. Now what is the angle between B bar and dl bar in this case? The angle between B bar and dl bar in this case equal to 0. Now in this case theta equal to 0 degree. So I can get the closed integral A to B bar dot dl bar equal to the closed integral A to B dl cos 0. Cos 0 degree value equal to 1. So here I can write the closed integral A to B dl. So B is non-integral terms. What is the value of closed integral A to B dl? So what is the length of the A to B? So here A to B length is considered as h, or it is easy to consider this term as L. So let me change this quantity as h to L. So for reasons I am changing that as L. Okay, take that as L, because when we remember formulas, so all formulas should be connected. Now this value goes to B times closed integral of dl, its value goes to L. Now I got what is the magnitude of magnetic field of this but is small portion, closed integral A to B bar dot dl equal to B times L. Let it equation 1. So likely we will find the second part. So now I am going to find what is this part, the closed integral B to C. Now in this case closed integral B to C B bar dot dl bar. How can I write that? Closed integral B to C B dl cos theta. Now here we need to bother about what is the angle between B bar and dl bar in this particular segment. Now in the B to C segment, means this is a segment. In this segment, the elemental length is perpendicular to magnetic field. So in the diagram, so the elemental length dl, if I draw elemental length with this bold ink at here, so this is the elemental length dl direction, and what is the magnetic field direction? So this is the magnetic field direction. So B bar direction and dl bar direction, they both are perpendicular. So here I can take that cos 90 value. So cos theta equal to 90 degrees at here. So the cos 90 value goes to 0, it means that particular portion do not contribute any magnetic field. Here theta equal to 90 degree. Therefore, closed integral b, it is little b to c, and b dl cos 90 degree is equal to 0. So I can write that as component value. For the second case, closed integral b to c b bar dot dl equal to 0. So this is my second case. So let us see the same case, the same like that. We are having one more side, that is from D to A. So if I highlight that D to A also same. So from the D to A portion, so this is the D to A portion. The elemental length, I am highlighting the elemental length vector with the bolding. So this is the elemental length vector dl bar. And magnetic field direction. So magnetic field direction is always perpendicular in this case. So in this case also the theta equal to 90 degree. So 90 degree if you can take, so directly I can write that expression, third expression set here. The closed integral, this is from A to D, D to A. D to A b bar dot dl equal to also 0. This is also exactly the same, the third case. Okay, I am not repeating it here. The same case also will be followed here. The theta value goes to 90 degrees and cos 90 value goes to 0. That is that part contribution also 0. And so 3 portions calculated. We left over with 1 portion. So that is the C2D. Now this I am going to take with this purple color. So this portion we need to calculate. Now in that portion, if you take the Amperian loop, the elemental length and Amperian loop. Yeah, the elemental length having the direction. If I draw the direction elemental length, oops, it's 180 degree. So this is the elemental length dl direction, and if you can see right in the diagram itself, there is no magnetic field line which are drawn at there. So there is no magnetic field lines in that particular portion. If you can say clear cut at there, there is no magnetic field line which drawn at there. So we will take at here magnetic field. At point Q, magnetic field B equal to 0. There is no magnetic field. That's what we need to consider if far away from the loop. So the Amperian loop is in a particular portion where there is no magnetic field. Yeah, because the Amperian loop is a closed loop, it cannot avoid that particular part. So in that particular portion, the B value goes to 0. Since B equal to 0 at out of the loop, remain careful at here. So you might be thinking that what happens if you consider Ampere loop very close to the coil itself. Yeah, by the time you can get it. But to cover entire solenoid, we need to consider a large Amperian loop. In the large Amperian loop, if you consider that, the particular portion will be go away where the magnetic field almost all negligible to 0. So the B equal to 0 at out of loop from the portion from C to D, that is from C to D. So what we can get in that equation? So we can get that equation at here. If we can write that the closed integral of C to D B bar dot dl equal to 0. What is the reason here? Here B equal to 0. Let me equation 4. Now if I I try to find the closed integral from a to d of b bar dot dl equal to closed integral from a to b b dl plus closed integral from b to c b dot dl plus closed integral from c to d c to d b dot dl plus closed integral from d to a b dot dl. So in this entire expression, the magnetic field is only contributed, the closed integral b bar dot dl from a to d is only contributed from only one part. So that is from this portion. From the first equation, this value I got that as b dot l. So don't be confused that here I have changed that. So this I can write, which equal to b times l, and the rest of three components magnetic field contributed goes to 0. So that's you understand from the equations how we fragmented that Amperian loop and how we find that elemental length and magnetic field direction and how these values become 0, because the angle between magnetic field vector and elemental length vector. So in the two cases, from B to C and from D to A, that angle become 90 degree, so that contributes 0. But in the case from the C to D, so this case, the magnetic field we have taken that as 0 itself. Now finally, this we need to make it equal. Closed integral b bar dot dl according to formula equal to mu naught times current I, current enclosed. Okay, so now I can write this as, in the place of b bar dot dl, I can write that b times l equal to mu naught times I. Now we need to write the magnitude of magnetic field. B equal to mu naught times I upon L. Here I current enclosed. So this is a formula for a solenoid, the magnitude of magnetic field. Now here I would like to do one small change. That change is, since the solenoid is made up of so many number of turns, so we need to include that, because if we can increase number of turns, common sensely the magnetic field strength increases. So that character also we need to include in this formula. Suppose the number of turns in length L of solenoid. Suppose the number of turns in length L, number of turns length L of the solenoid, I can take that length L capital N equal to small n times, that is number of turns, times total length. Suppose the number of turns in length L. Suppose if I taken this is the length L. So in this one, how many turns are there? Suppose 3, 4, 5, 6, 7, 8, 9, 10. So in this length L, how many turns are there? I have taken 10 turns. So the total number of turns here equal to 10. The number of turns in the length L. So from this, if I write the number of turns per unit length, the number of turns per unit length, whenever you can calculate per unit length, So that is nothing but small n per unit length of solenoid, that equal to small n. Okay. Now through this number of turns, total number of turns, here small n becomes number of turns per unit length, and through those many turns how much current is flowing? Now the current threading, the current passing, the loop, here the loop I consider that A, B, C, D, A. Through this loop, how many turns are there and how much current is passing? Through that loop, how many turns are there? The number of turns per unit length times total length of the coil, and here the current is passing, so here we need to multiply with that current I. So try to get this carefully. So because what the Ampere loop we consider, that is having number of turns, so that number of turns, through that and the amount of current which is passing. So now this I replaced in the term current enclosed, because the Amperian loop is enclosing those many number of turns. Now this formula, if we can rewrite it here, the magnitude of magnetic field B equal to mu naught times, here the current enclosed equal to N times L upon I divided by L itself. Now you can cut the total one common factor, that is L. Now this expression became more simple, mu naught times N upon I, mu naught Ni. Okay. Now how can we relate how the magnetic field strength increases? From this formula we can understand magnitude of magnetic field is directly proportional to strength of the current, and magnitude of the magnetic field is directly proportional to number of turns per unit length. So here small n is number of turns per unit length. In one unit length, how many turns you increase? It means if you can increase so many turns in one unit length, the magnitude of the magnetic field is also increases. So this is the final expression for magnitude of the magnetic field for a current carrying solenoid. So I can write that expression B equal to magnitude of magnetic field B equal to mu naught small n times I. So here remember, at small n equal to number of turns per unit length. Therefore the magnitude of magnetic field B is directly proportional to I. B is directly proportional to I. When current increases in the solenoid, the magnetic field also increases, and B is directly proportional to small n, means the number of turns per unit length. And to find the direction, we are using the right hand thumb rule. So the right hand thumb rule gives the direction of the magnetic field. So one side will be acts as north pole and another side will be acts as south pole according to natural magnet. So this is all about an application of Ampere's law, current carrying solenoid.